All right, hello and welcome to lecture number 21 of CS135. So before we get back into discussing the various things about generative recursion, a few things I should make note of. One is that if you've had any issues submitting assignment 8, please make sure that you send a message to Roger or Ben, our wonderful ISAs, and they can direct you in what to do next. Secondly, don't forget that you do have an assignment 9. It is a rather short assignment 9, and it is due this Friday at midnight, I believe. Well, 11:59 p.m. And the focus of assignment 9 is, of course, using abstract list functions. You're not going to have any assignments on graphs or anything like that. So if you're sitting there panicking, like, oh my God, what am I going to do? Because we haven't even covered graphs yet, don't worry about it. Although it is completely coverable content for the final assessment. And speaking of the final assessment, we will actually have more details about that coming in the next few days, hopefully by the end of the week. And just to give you a heads up, the final assessment we've kind of stated is optional. You're going to get the maximum of 2 grading schemes. I highly recommend you do the final assessment because the only thing it can be used for is to boost your mark. All right, so that's really all the announcements we have for today. So let's go and do some review then. So we ended last class talking about generative recursion, but before that we actually finished the module on abstract list functions. And I want to go back and I want to look at a problem that we solved manually using recursion, and I want to see if we can improve upon that. So what you'll see here that I have on the screen is I have an implementation for insertion sort. So the first function I have here, this is the insert function that consumes an item and a list that is sorted, and it's going to insert the item into the sorted list so that the new list is also in sorted order. Now in this particular case, we're only dealing with lists of numbers. Now this function is used by the insertion sort function, which I've just called isort here. And what isort does is it's going to process the input unsorted list element by element and insert them, each of those items, into a sorted list. And we're going to start by passing in an unsorted, a list of nothing to insert. So that is our insertion sort. And it's very, very simple, as you can see. We've got here total lines of code. I've got 7, so not that bad. So let's actually do some evaluation of this code. Well, first off, a lot of you might be thinking, and if you have read through the slides, you might be like, well, we were told that this insert helper function should probably be localized. And I want to say I disagree with that. You might be thinking to improve the quality of this code, to improve the maintainability of this code, to improve the generalization of this code, we should make this a local function. And the answer is actually no, you shouldn't make insert a local function, because insert is a function that is useful to many. It's not just useful for something like insertion sort. Presumably, you are using insertion sort because you're given an unsorted list of things and you want to produce a sorted list of things. Well, after you have a sorted list of things, every time you insert something new, do you want to be calling insertion sort again? Because that's really inefficient. So what you want to do is you take an initial group of data, you sort the initial amount of data, and then you're going to want the ability to insert a new item into a sorted list of data. So this insert function is actually a very useful function, not just for insertion sort, but presumably for many other functions, like maybe we are trying to sort a list of students. Well, once I have a sorted list of students, my add function needs to be able to add a new student to the class in sorted order. So it would need insert. So it's useful as a helper for many other functions, but this is also conceivably a function that a user would find very useful. So while the slides might suggest that you should make insert local, you absolutely should not make insert local. It should be something that's provided at the top level because it is useful in many, many different situations. Okay, so there's two things we want to do with this code. We want to simplify this code. We also want to make this code a bit more general, because right now this code actually only works on integers. So let's take a look just at, for now, our insert function. How can we improve this? Well, interesting thing, you might be thinking to yourself, well, I'll just replace it with a folder. And I'm not saying that you can't do that, but I am going to say it's not trivial, because if you look at the kind of recursion that insert is doing, it doesn't have just one base case where the list is empty. It actually has two base cases. So the first base case is that the list is empty, which is the standard simple recursive base case. It's a little bit more complicated though, because there's a second base case in the fact that the item you're trying to insert is less than the first of the list, which means we need to cons the item we're trying to insert onto the list, and we are done. So I'm not saying you can't use folder to simplify this. I'm saying it's not trivial. And I'm actually going to leave that as a challenge to you on your own. Can you take insert and can you make it use abstract list functions? That's not what I want to focus on. The part I want to focus on with the insert function is the fact that this insert is restricted to using numbers. And it's restricted to using numbers because we are only using the less than operator, which only works on numbers. Okay, so I want to abstract this insert function. So let's make an abstracted insert function. Now what we are going to abstract is the only part that actually works on a specific type. And that is, we're going to abstract the comparison operator. And we're going to turn that into a parameter. So for lack of better names, we're going to call this insert2. And we are going to, in addition to consuming the item we're inserting and the sorted list, we also now want to consume a comparison function. So comp will be our comparison function. Item is the thing we are inserting, and slist is going to stand for sorted list. And our function actually looks very much the same. Except instead of doing less than, we're going to do the comparison function and apply that. And our recursive case is the same as well. Make sure that you call your new function and not the old one. There we go. Now let's run that. Now here's the thing. We've just written a function, and you'll notice I haven't put any of the design recipe in. That's in the interest of time. But we should still show some tests for this abstracted insert. So the obvious one that I would do is I would give a few tests. One test I would do for, well, let's actually make them check expects here. So let's do check expect insert 2 less than. Now I want to try to insert something into an empty list. So let's do that. I want to insert 5 into empty, and I want that to produce a list containing 5. Let's make some space here. Another test I want to make sure that if the thing I am inserting goes to the front of, should be put at the front of the list, it is put at the front of the list. And I also want to make sure if the thing I am going to insert should be at the end of the list, that it indeed goes to the end of the list. And now I want to choose an element from the middle. So those tests there kind of cover the 4 different cases that we have. Now there are other tests that you could certainly do. For example, insertion sort or insert. Actually, what's interesting is you can have duplicate entries and it should work just fine. So maybe we want to test that just to prove that it does indeed do what we expect. So let's choose 2. Okay, that is a very complete set of tests for working with lists of numbers, but we haven't written a function for a list of numbers. What we've written is an abstract insertion. So we should try just to make sure that it works for other kinds of comparison functions. Let's try some other ones. So yes, this is a lot of tests if you were wondering, but how else can you prove to not just yourself, but to the user that this function does exactly what you say it does? So let's do string less than, and I want to insert ABC into that list there. And, maybe I don't want to sort the items in increasing order. Maybe I want to sort them in increasing order. And that's one of the cool things about abstracting this insertion function, is you define the order. So let's put things in increasing order. And again, we're going to use just regular numbers here for this particular test, but you could have used another operator as well. Okay, so let's run this. And there we go. So we know now that our abstract insert function works quite well. Now, again, I want to leave it as an exercise to you to see, can you take our insert function and further simplify it by using some of our abstract list functions? It's not easy, by the way. I'm going to leave insert there. Now I want to address my insertion sort function. So here we have the one that is not general because it only works on integers. It also is using straight up simple recursion, like literally. And you can see it follows that simple recursive template. If the list is empty, we produce something. Otherwise, we're going to do something with the first element, and then we're going to process the rest of the list. Okay. Well, this is a key function that not only we need to generalize so that we can pass insert the appropriate comparison function. So we're going to need to add an extra parameter, but we can also use very easily an abstract list function to turn insertion sort into something very simple. So let's make our isort2. And now it's actually going to take a comparison function, even though this function doesn't use it. We need to consume it so that we can pass it to insert. And now we are not going to do explicit recursion. We are going to let fold R do the work for us. And that's it. So what have I done? Well, remember that fold R is going to process elements of the list one by one, going from the right to the left. So, and then the Y argument is going to be the results of running this function on the rest of the list. So what I want to do is I start out with my sorted list as being empty, and then I'm going to one by one call insert of the current element into Y, which is the results of sorting the rest of the list. So I'm going to call insert2 with comp on X and Y. All right. You can see there's no syntax errors. Now, what kinds of tests would we do for this? Well, here's a few that you might consider. I want to make sure that if I pass isort a sorted list, that is a list that is already sorted, I get the same list out. That makes sense. And oh, you know what we forgot? We forgot our comparison function. So let's add that in. I also want to make sure that if I give the function a list that is sorted in the opposite order, That is, we wanted it in increasing order and I was provided a list in decreasing order. We want to make sure that that works as well. And I also want to make sure that an empty list produces an empty list. And I want to make sure that if my list contains a single item, that my sorted list also contains that sorted item. And maybe I also want to test the generalization of this function, so let's do something other than numbers. Oh, I don't want to do chars. Chars are a pain. Let's do string less than. All right. Now, what order should this be sorted in? Remember that strings are sorted in lexicographical order, i.e. they're sorted in ASCII order. So the string that the list that I expect to come out of this is actually barbecue, ABBA, cat, helps if I can spell, and then dog, and then R2D2. Okay. And there we go. We have written a new version of insertion sort that is abstract and is a little bit simpler. So instead of our 7 lines of code, we've actually taken it down to 6, and it's abstract. So that's actually pretty cool, and it's thoroughly tested here. All right. So I'm going to switch over to some other slides here. Go. And let's just move this down here, just for now. Okay, so here's what we've got. At the end of last class, we introduced you to this concept of generative recursion, which wasn't actually new. We've mentioned it before. But let's actually think about some of the properties of generative recursion. So first off, we have this question. Generative recursion differs from simple and accumulative recursion. And you've got 4 options here. So we say first, each recursive application moves 2 or more steps towards the base case. And if you recall, generative recursion, well, simple recursion, each recursive application moves exactly 1 step towards the base case. And generative recursion was supposed to be not. So it's very conceivable that A is the answer, but let's keep reading the possibilities. So then we look at B, which says each recursive application moves 1 or more steps towards the base case. Maybe that sounds a little bit more accurate, because maybe we do sometimes move exactly 1 step, and maybe sometimes we move more. It really depends on the function that we're implementing. So let's keep going and see if any of these other options are better. Each recursive application may move toward or away from the base case by some number of steps. And then D says none of the above. Now, I know a lot of you are probably thinking that the answer must obviously be B, but it's not. The answer is actually C. So why is it C? Well, our recursive applications are based on whatever function it is we are implementing. And in some cases, we may be moving away from the base case, and we might be moving towards the base case by some number of steps. And if you can't think of a time where you're moving away from the base case, I'd like to remind you of our good friend, the Collatz conjecture. And what this was a recursive function where if you call Collatz on n, and n is even, it calls Collatz on 3n, or n divided by 2, which would be moving us towards the base case of n equals 1. But if n is odd, we don't move towards the base case at all. We call Collatz on 3n plus 1. And what's interesting is that we don't even know if this terminates. And this is actually an outstanding problem in computer science, is does the Collatz conjecture actually terminate? We don't know. And the recursive applications, we don't know if they're moving towards the base case or not, because we don't even know if it terminates. And this is actually generative recursion. So generative recursion, each recursive application may move you some number of steps towards the base case, and it may not. And it really depends on what problem it is you are solving. Now, of course, the Collatz conjecture, why are you even doing this? It's just one of these, like, I'm bored and I'm at home and I have nothing to do, so I'm going to prove the Collatz conjecture. And maybe that's you right now because you've been home for the last 2 weeks and change and you're probably bored out of your mind. Well, go ahead and prove the Collatz conjecture. And maybe you'll be famous. All right. So what I want to do is, instead of going on to our last little problem in the slides, I'm going to go back to Racket. And I want to do another example of generative recursion, because we don't actually have a lot of examples of generative recursion. So I've implemented this function skip, and skip is very silly. So if you're wondering why it does what it does, I don't know, I just made up a function that is generative. So what skip does is it has a base case where n is less than or equal to 0. And if that is the case, we produce empty. Otherwise, if n is even, we're going to cons n onto calling skip of n over 2. And if n is not even, then we're going to cons n onto subtracting 1 from n. Now, what's interesting is that we have to think about with generative recursion, does this terminate? This does terminate, because in both our recursive applications, we can see we are making progress towards a base case. If n is even, we divide by 2, which is going to take us closer to 0. And if n is odd, we subtract 1 from n, which takes us closer to 0. So we know skip terminates, and it's quite easy to prove that. But how deep is the recursion here? Because sometimes we're dividing by 2, and sometimes we're subtracting 1. So let's actually run this a few times so you can see what it does. It's kind of boring. So let's call skip, and the easiest answer is let's call skip on a power of 2. So let's do 128. That's a power of 2. And you can see here we get the list 128, 64, 32, 16, 8, 4, 2, 1. Which is dividing by 2 until it reaches 1, in which case we subtract 1 and we reach the base case. So if this was using simple recursion, there would be 128 recursive applications. But because this is generative recursion, we've actually only done 1, 2, 3, 4, 5, 6, 7 recursive applications. So that's kind of neat. Now let's do an odd number. Maybe not an odd number. Let's do something out there like a prime. So this is a fun one. So we did 67. So that produces 67. And then we subtract 1, which gives us 66. Now that's an even number. So we divide by 2, which gives us 33. 33 minus 1 is 32, which is now a power of 2. What's interesting about this is we have 1, 2, 3, 4, 5, 6, 7, 8 recursive applications for a smaller number. It's kind of cool, right? So this is a generative recursive function. But again, this is totally not useful. Now, if you wanted to produce all like the powers of 2, going down from a maximum to a minimum, maybe that's a useful function for you. Then that's also a generative problem that's very similar to this one here. But this function here is not useful. So I want to talk about a kind of problem that is generative recursion and is actually very useful. And that is divide and conquer. So what is divide and conquer? So the first option we have here is it takes a hard problem and divides it into easier subproblems, then combines the result. That sounds like divide and conquer. Then we have B, it can only be achieved with map and foldr. Well, it definitely can be achieved with map and foldr, but are there other ways of implementing it? Well, obviously, the answer to that would be yes, because I can implement map with foldr. So technically, we could say it couldn't be achieved with foldr, but and since there are 2 ways that we could do it, it's not the only possibility that you can do it with map and foldr. is only useful for sorting. Now that might be a tempting one to think is true, but actually that's not true. Divide and conquer is actually, well, it's actually, it's useful everywhere. Think of it this way. Suppose I want to play with an image. An image has a lot of little pixels, millions of pixels. Okay, so I could just process each pixel one by one by one by one, and it'll take a really long time. But what I actually want to do is if I subdivide the image into smaller images, and I process the smaller images in parallel, that means at the same time, and then I combine the results all back together again, I can process that image a lot faster. That's actually using MapReduce, which is a divide and conquer strategy. So the answer here is actually A and B. The wording here is careful because B says can be achieved, not can only be achieved. So divide and conquer does take a problem that is hard and divides it into smaller problems that are easier, and then we solve the easy problems and combine the results together. And one of the ways that you can implement a divide and conquer algorithm is through use of map and folder, which for anyone out there who's interested in things like MapReduce or Hadoop, map and folder kind of create a MapReduce. Now, it's not like real-world MapReduce, which does things in parallel, but it has the same idea, just not the parallel part. All right. So, talking about divide and conquer, one of the things that we should point out is that divide and conquer is useful for sorting, and many sorting algorithms that we use actually use divide and conquer. And in fact, so the one we talk about in the course notes is Quicksort. So let me just bring this over here, and we will bring it to full screen so you can see it. So this was the Quicksort algorithm that we have. And what Quicksort is going to do is Quicksort takes a list, and a list is hard to sort. And we're going to keep dividing it into two and sort the smaller lists. And then after we have all the individual teeny lists sorted, we combine the lists together in sorted order. So we've subdivided into an easy problem and then combined all our easy solutions back up into getting the big solution. And Quicksort is a divide and conquer algorithm, and it's very closely related to another divide and conquer sorting algorithm known as merge sort. But Quicksort in practice has a tendency to be faster than merge sort, even though they are very, very similar. And what might blow your mind even more is that insertion sort is also a divide and conquer algorithm and is a special case of Quicksort and merge sort. So let's go and let's discuss Quicksort by looking at an example. So with Quicksort, what we're going to do is we take a list and we are going to divide the list into two sublists. So in order to choose how we divide the lists into two, we're going to choose what's known as the pivot. And for the purposes of this course, we always choose our pivot to be the first element of the list. So we'll write this here. So that was our step one, is to choose a pivot. And in this case, we choose the first of the list. So we're going to choose 3 to be our pivot. And then in step 2 of Quicksort, we are going to subdivide the list according to that pivot. Everything that is smaller than the pivot goes in on the left list, and everything that's bigger than the pivot is going to go into the right list. So to show you this, so what we end up getting is the list 1, 2, and then the pivot 3, which is not a part of this list. It's not a part of any list now. And then we have so that's on the left, and then on the right, we're going to put everything that's bigger than the pivot, which in this case is going to be 6, 8, and 9. Okay. Now we need to call Quicksort on these two sublists. So I'm going to do this in parallel, although in Racket this wouldn't actually happen in parallel. So we're going to, again, for the left, we're going to choose a new pivot. And my new pivot is actually going to be 1. And so the things that are smaller than 1 are nothing. And the things that are greater than 1 are 2. And then so now I've processed my left sublist. Now let's process my right sublist. So I choose 6 to be my pivot, which leaves us with no items in the the right subproblem that are smaller than 6. And we have 2 items that are bigger. And now we're going to call Quicksort again on these sublists. Now what's interesting is that if you have a list of 1 item, you don't really need to call Quicksort on it because it's already sorted. And if your list is empty, you don't need to call Quicksort on it because it's sorted by virtue of the fact it's also empty. So we're actually going to leave those ones alone. And the one that we're going to call it on now is we're just going to call Quicksort on this sublist that we have right here. So we end up with choosing 8 as our pivot, and then we have no items smaller than 8, and we only end up with 9 that's bigger than 8. So now we have actually sorted all of our sublists, we've reached our base cases, and now we need to combine the answers all back up together. How do we combine a bunch of sorted lists together? Well, actually, all we need to do in this case is call append. That's all we're going to do. We are just going to append all these lists together, and we end up with 1, 2, 3, 6, 8, 9. That's Quicksort. Now, if you're wondering, how is this a generative recursive problem? Well, the reason why it's generative recursive is because we are making a recursive call, not moving necessarily 1 step closer to base. We may move 1 step closer to base, or we may move 2 steps closer to base, or we may move directly to the base case. The number of steps that we move towards the base case with each recursive call depends on the pivot that was chosen, and it depends on the list that you are subdividing. Now, an important thing to consider is, does this terminate? The answer is yes. Quicksort does actually terminate, and it's very easy to show. There's a proof in CS240 if you're interested, but very, very briefly, we need to show that with each recursive application, we are making progress towards the base case. And is that the case? Well, it is, because even if everything is bigger or smaller than the pivot, we are still removing the pivot from the list, which means in the worst case, the list we are calling Quicksort on is decreasing in size by 1. In the best case, the size of the lists we're calling Quicksort on are decreasing in size by half, but that's the best case. Now, merge sort, as I said, is the other well-known divide and conquer algorithm, and it's very, very similar to Quicksort. How it works is, instead of choosing a pivot, we're just going to use merge sort to divide everything into lists of equal length. So we would take, with merge sort, 3, 1, 6, 8, 2, 9, and we would divide that into 2 sublists, 3, 1, 6, and then we would also call merge sort on 8, 2, 9. And then that's going to divide into lists 3 and 1, 6, and then 8 and 2, 9, and then we call merge sort again on each of these sublists. Now, it just so happens that 3 is the smallest you're going to get, and then we get 1, and then we get 6, and then we get 8, and then we get 2, and then we get 9. So this is just recursively subdividing until each element is in its own list. And then what we do is, on the way back up the recursive tree, i.e. on the return part, we're going to merge 2 sorted lists. So then we're going to take 1 and 3, and we're going to turn that into 1, 3, and then we're going to take, well, actually, that's not how those two would go. We would end up with 3, and then we would end up with 1, 6, and then on the other side, we would end up with 8 and 2, 9, and then we would end up with 1, 3, 6, merging those two lists, and then 2, 8, 9, and then we would merge those two lists to give us 1, 2, 3, 6, 8, 9. So that's merge sort, and that is very, very similar to quicksort. But on average, it's actually slower than quicksort by a teeny tiny bit. Again, proof CS240. And what I want to tell you is that insertion sort is also technically a divide and conquer problem. See if you can play with insertion sort on a piece of paper and see why it would also be considered a divide and conquer problem. And the hint I'll give you is think about how merge and quicksort divide into smaller problems. Okay. Now, merge sort and quicksort are both generative recursive algorithms. Quicksort, we've already talked about. Merge sort is also a generative recursive algorithm because we are moving towards the base case at a rate of n over 2, where n is the length of the list, because each time we call merge sort, it's on a list that is of size n over 2. So that means that you are going to end up calling merge sort log n times. Does that mean that merge sort's runtime is log n? No, it's actually n log n. Exactly n log n. And for the record, quicksort is actually, in the worst case, as bad as insertion sort, so n squared. But in the average case, it's also n log n. And in practice, we see that quicksort behaves that way most of the time. Again, CS240. We don't expect you to know that. All right. So then, I feel like that is sufficient review of where we left off last class, and I'd like to actually work towards finishing up our module on generative recursion. So, one last thing I want to make note of is with generative recursive problems, it's very, very critical that you know inside and out the method that you are trying to implement, because it's so easy to screw up the recursive applications and the base cases and end up with infinite recursion. For example, with our quicksort termination, we know it terminates, and it's very easy to prove that it terminates. But if we accidentally subdivided our lists using less than or equal to the pivot instead of less than, we would actually end up with infinite recursion. And the reason for that, not all the time, but there are cases where we would end up with infinite recursion. And the reason for that is we wouldn't be removing the pivot from the list. So in the worst case, we would call quicksort on a list of n items and then quicksort on a list of n items, and it would just repeat forever. And if you're wondering what would produce that worst case, that would be a list that is already in sorted order. That would produce the worst case with infinite recursion if we made this teeny tiny mistake right here. So it's very, very important you pay attention to recursive applications and base cases with generative recursion. All right. So, do we need to modify our design recipe in order to do generative recursion? Not strictly speaking, there's no special thing we need you to add. But we would like to highly suggest to you that you should provide additional documentation to describe how this function actually works. So in addition to the purpose and the contract and the examples, you should also describe how this function actually works so that anyone reading it can look at it and be like, okay, I understand what's actually going on here. Because if you look at generative code, it doesn't follow the data definition. It doesn't follow the template. So it's not always obvious as to how the method works. So it's really important for generative recursive functions that you give some additional documentation to say, how does this actually work? Can you prove to me this terminates? All right. Now I'd like to do one more example that's actually a really fun example. And that is to, if you're given a body of text, suppose you actually want to take that text and divide it into lines. And we're going to assume that we've written, just one sentence on each line. Now, how do you know whether you have a new line or not in a body of text? Well, in regular text, we use this \n to represent a new line character. And when a computer renders that, it would put AB on one line, and then on the next line, it would put CD. And in Racket, there is a special character called #/new line that is the new line token. So I want to take a body of text and I want to produce a list of text where it's been separated by lines. So for example, we have this one here. We've got 1 new line, 2 new line, 3, and that's all one string. And I want to produce the list 1, 2, 3. So each line is its own string in the list. And I want to remove those new line tokens as well, because maybe I want to do some other processing on this body of text. And if you're wondering, why would anyone want to do processing on a body of text? This is how targeted advertisements work, is because they are recording the things that you type on Facebook or the things that you search for on Google, and they're doing some text processing on that and using that in a big ML model to figure out people who have this kind of writing style and these kind of keywords tend to purchase these kinds of items, so we should give you these kinds of ads. So text processing like this is super, super useful. And it has its own field. They call it NLP, or natural language processing. Very important these days for marketing, for security, for tracking pandemics. It's useful all over the place. It's something that I do research in, where I'm trying to estimate what is the value of a film script before we even make the movie. So can we guess, is this going to be a box office bust, or is this going to be a box office success, just from the text alone? So text processing, like what we're about to do, even though what we're doing is very simple, is actually a super useful thing. So, okay. We're going to do a generative solution to this because it's actually much easier to do so. So what we're going to do is we're going to give a higher level data definition, actually. We're going to, instead of thinking of our string as a list of characters, we're going to think of it as a list of lines. So you have either an empty list of lines, or you have a line followed by a list of lines. And what I'm going to do is I'm going to implement 2 helper functions. One helper function to give us the first of the list of lines, and one helper function to give us the rest of a list of lines. And so here's the code for that. So this is first a line. And what this is going to do, this is, our data is now, instead of a list of characters, it's a list of lines. So I want to give me the first line from my list of lines. So I'm going to process my list character by character. And until I reach the first new line token, I'm going to keep consing the characters I have seen onto the result of looking for the new line in the rest of the list of characters. So first off, if our base case, if the list of characters is empty, produce empty, you're done. And our second base case is if the character that is at the first of the list is the new line token, then I am going to produce empty. We are done. And then if we look at this, we are going to then, in the recursive application, where this is not a new line and this is not an empty list, we are going to cons this character onto the result of searching for a new line token in the rest of the list. And hey, you know what? This actually follows a simple recursive template, so that's kind of cool. Yes, this is simple recursion here. Now, if you look at this, just to show you what it would do, is if you call first line on string to list ABC, NDEF, it's going to produce a list of characters ABC. And if you have A followed by a new line, it just follows A. And if you just have empty, it just produces empty. You will note that everything that follows, and including the new line token, is not produced by this. Okay. Now we need the function to get the rest of the lines. And to get the rest of the lines, we're going to need to ignore everything that precedes that first new line token. And again, this actually also uses simple recursion because each recursive application is making exactly one step of progress towards our base case. So if the list is empty, produce empty. That's standard. If the first of the list is the new line token, then this is our first new line. We have just finished processing it, which means the rest of the lines is equal to the rest of the list. Now, why don't we include the new line? Because we don't want it. So that's our second base case, is we've hit a new line token. The rest of the list is the rest of the lines. In our recursive application, we are simply going to call rest of lines on the rest of the list, which is why I'm telling you this is a simple recursive function. It's processing this list of characters one by one. We just have an extra base case here. So in our list where we have a new line, there are no remaining lines, so we get empty. And if we have a new line B, we just get B. Okay, so we have a first for our list of lines, and we have our rest for our list of lines. So what are we going to do then? Well, we have this high-level template, this high-level data definition. We can make a template for it. So we could say, okay, well, we're going to say that the first line is equal to, we've got some local definitions here, which I kind of feel are totally unnecessary, but that's up to you. And then we've defined this is the first of our first line of our list of lines, and this is the rest of the lines from our list of lines. And then, hey, this looks like a simple recursive template because we've got if the list is empty, empty. Otherwise, do something with the first line and call this template on the rest of the lines. And it looks like simple recursion, but this is not simple recursion. It's just not. Now, you might be having a hard time of thinking, why is this not simple recursion? Because it looks exactly like it. But the thing you need to keep in mind is that first line and rest of lines, while those were simple, if we are now using those two functions to process a list, each application of that does not move us one step closer to our base case because our list is not a list of lines. A list of lines is some arbitrary high-level definition we gave it to think about the problem. We actually have a list of characters, and a list of characters, we process this list one character at a time, and that is not what we are doing here. We are processing it one line at a time, and the lines can have different lengths, which means that we are processing this list at different rates depending on the length of each of the lines. That is the number of characters between the new line tokens. So this is not simple recursion. Now, however, the template is useful. We can take it and we can fill it in and get our final function. And again, this is actually making use of a list of characters. So make sure that you use string to list and list to string as appropriate. So first off, again, we've put in here a nice data definition, or not a data definition, a constant for the first line and a constant for the rest of lines. And then if the list is empty, produce empty. Otherwise, cons, turning the first line into a string onto the result of calling this list of characters to a list of lines on the rest of the lines. Looks like simple recursion. It isn't, because we are processing this list of characters at different rates depending on how many characters are in between each of those new line tokens. But it's a really simple function, right? Once you think about it, it's not a complicated function. Now, of course, one of the things we have to ask ourselves is, can we make it simpler? Yes, actually you can. There was no need to do all that local garbage, as I suggested earlier. You can get rid of it entirely, and in fact, I would suggest it because there's absolutely no advantage to having that local definition there other than to make your code really ugly. So you can just call first line and rest of lines directly where they are. Now, the big question that we have to ask is, does this function terminate? And the answer is yes, it does terminate, because at no point are we increasing the size of the list. We are always decreasing the size of the list by at least 1. So we are eventually going to make it to the base case. So this does terminate. That, again, is one of the hard things to think about generative recursion is this going to terminate or not? All right. Now, you might have been wondering, can you implement this using simple recursion alone? Actually, yes, you can. As you can see, it's on slide 27 here. This is ugly. This is so hideous. We've got locals, we've got inside of else conditions. It does work. And we're using abstract list functions, but this is really ugly. It's a headache to try to understand what's going on here. I'm not going to sit here and explain this to you because I don't really think that's very useful, but I do encourage you to take a look at it and see, can you figure out what this is doing and compare the simplicity of the generative recursive solution to the simple recursive solution. Sometimes generative recursion is much, much, much easier to work with than simple recursion. Even though we can't create some template for it, even though thinking about termination is harder, it doesn't mean that generative is always harder than simple. Sometimes the generative recursive solution is actually easier than the simple one. All right, so that is actually the end of our generative recursive module, which leaves us with just one module to go. Now, just keep in mind, technically speaking, if you go on the course website, yes, there are 2 more modules. We are not doing module 17, the computing history. And this does actually make me quite sad because I love computing history, as anyone in CS135 will know. But we had to cut 1 week's worth of material. And so I asked myself, what material is going to give you the best education moving towards either CS136 or a programming job? And I had to decide between graphs and computer history. And it's good to know who Alan Turing and Grace Hopper are, but that's not going to help you program. So we're going to now move on to discussing the wonderful world of graphs, which maybe some of you don't think is a wonderful world, but I like it. All right. All right, so graphs, that's module 16. We're going to go through some of this content a little quickly, and hopefully next lecture I'll actually be able to draw a little bit neater. We'll see what happens here. So first off, what is this mystery thing called a graph? Well, actually, you've been working with graphs for a good part of this term and didn't even know it, because a tree is technically a special kind of graph. So what is a graph then in general? A graph is a bunch of nodes or vertices which may or may not be connected by some edges. Now, there are many different kinds of graphs. There are things called connected graphs, which means every node is connected together. Not every node has a connection to every other node, but there are no parts of the graph which are not connected to the other ones. A tree, for example, is a connected graph. There are no nodes just sitting out there in the middle doing nothing, connected to nobody. There are no orphans. There are also disconnected graphs, in which case there are parts of the graph which are not connected in any way to other parts of the graph. For example, a forest of trees is a disconnected graph. Trees, as I said, they are graphs. There are also directed graphs like we actually have on this slide, and I'll talk a bit more about them in a minute. There's something called an acyclic graph. There are cyclic graphs. There are directed acyclic graphs. There are many, many different kinds of graphs. And graphs are very, very important to computer science. There are so many problems that make use of graphs that it's actually a really, really important topic. And it's one of those things, you'll do it in CS135. You may not touch it much in CS136, but CS240 you'll see a little bit. You'll do a lot of graph work in CS341 and Math 239. And then moving on from there, you may see more and more graphs depending on where your interests lie. Now, if you're curious to know, where would I be using a graph? Well, suppose you are Canada Post, and Canada Post, of course, has to deliver mail between not only just all the houses, but we have to deliver mail from the Kitchener Depot to the Waterloo Depot, and the Waterloo Depot to the Toronto Depot. And you could just, let's consider each of those cities to be nodes. And you could just say, okay, there's a truck of mail that needs to go to Toronto, just drive to Toronto. But you have to ask yourself, is there a more efficient path that you could take through the cities such that you save money? And that's a graph problem. It's actually a quite famous graph problem. And some other things that are graph problems are flood fill. So maybe when you were younger, you open up MS Paint, and I remember when I started using Windows, it was like Windows 1 or Windows 2. I don't even remember. It was so long ago. And the tool we all wanted to use was this paint program, because we never had a paint program before, and it's so cool. And you scribble on the page, and then you get out the flood fill, so you'd start flood filling the regions. Flood fill uses graphs to fill all the pixels. Each pixel is a node in the graph, and the nodes that are right beside you are connected by edges. And how you do flood fill is by doing a graph algorithm. So graph algorithms, they're all over the place. They're used for computing efficient paths. They're used in networking, like a computer networking. When you send an email, how do you make sure that email gets to your friend's computer on the other side of the world? What path does that packet of data go on from you to them? And you might be thinking, well, the shortest path. Except it's not quite that simple. We have to think about things, well, what is the most cost-effective path? And we have to think of things like, oh, I don't like that country there, so I'm not sending network traffic through there. So graph problems are everywhere in your life. So it's really, really important to get excited about them. Maybe I get a bit too excited about them, but I also teach networking sometimes, so you'll have to forgive me for that. So we're going to work with a fairly simple kind of graph known as a directed graph. And what a directed graph is it has nodes or vertices, and they're connected by edges, but the edges have a direction. So you'll see here we have node A and node D. And node A has a directed edge from A to D. That means we can travel from A to D, but not D back to A. So this would be like having a 401 that is one direction from Waterloo to Toronto. You can go from Waterloo to Toronto, but you can't go the other direction. So a directed graph, the edges have a direction, and you can only follow that direction. How we normally represent an edge is we would use the node pair or the vertex pair, AD, and that indicates there is an edge, a directed edge from A to D. Now, I'm going to skip slide 3 here because it's not really important or interesting. And let's move on to a bunch of terminology. Now, in a graph, as I said, each of the actual nodes or vertices have some number of edges. Now, you can have nodes which are called adjacent to you, or a neighbor. And an adjacent or a neighboring node is a node that you are connected to by an edge directly. So for example, in this particular graph here, the adjacent nodes to A, or the neighbors of A, are C, D, and E. And only C, D, and E. Now, because this is a directed graph, we have two different terms for neighbors. There's something called an out neighbor. That is, those are the neighbors of A that we can go from us to them. So the out neighbors of A here are C, D, and E. So we can go from A to C, A to D, and A to E. Those are our out neighbors. Then we have what's known as an in neighbor. Those are the nodes which go to us. And you can see here that A actually has no in neighbors at all. But let's find a node in here that does have an in neighbor. D, for example, has an in neighbor. So D has two out neighbors, F and J, and it has one in neighbor, and that's A. Now, so that's neighbors. Then we have what's known as a path or route. So I can find paths through a graph, and we specify a path by taking the list of the nodes that we travel in order. So for example, if I wanted to create a path from A to K, the path would be A, E, K. Now, what's interesting is there's actually two paths from A to K. There's A, E, K, and there's also A, D, F, K. And that's an interesting thing about graphs. Graphs can contain multiple paths to the same thing. That makes sense if you think about it. If you wanted to drive from Waterloo to Toronto, for all you know, you could drive to California and then from California to Toronto. That's technically a path to Toronto from Waterloo. Also a really dumb path, although a really fun one, I might add. Okay, so a path is going to be a list of nodes, and we say that the path has a length k minus 1. Now, what does that mean? Well, what we're saying is if there are k nodes in the path, then there are k minus 1 edges. And we use the count of edges to determine the length of the path. So the length of the path AEK is 2, and the length of the path ADFK is 3. Now, even amongst this, there's two kinds of directed graphs we could describe. There's something called a cyclic graph and an acyclic graph. What a cyclic graph is a graph that has a circle. That is, I could go from A to B to C back to A. I can continue going around in a loop. Graphs that have cycles in them can be very difficult to work with because if you're trying to find a path and you've got a cycle, how do you know when to stop going around in a loop? It can be very, it's possible to do that. There are algorithms that work with it, but there's more thinking involved. We're going to work with acyclic graphs, which means this graph has no cycles in it, no loops. We can't go A, B, A, B, A, B forever. That will make life a lot easier. Now, how are we going to actually represent our graphs? For the record, there are many, many different ways that we can actually represent a graph. One of my favorite ways of representing a graph is using something called an adjacency matrix. We're not going to work with an adjacency matrix, but you'll see it later on. There's also things like adjacency lists and so on and so forth. So we are going to use the adjacency list, and what it is going to be is each node is going to be represented as a pair. So our list's key is going to be this node, and its value is going to be the list of the out neighbors. We are not going to keep track of the in neighbors. We're only going to keep track of the out neighbors, because if you have an in neighbor A, that means you are in somebody else's out neighbor list. So there's no point in keeping track of your in neighbors because that will be somebody else's out neighbors. So we're going to keep track of each node as a pair, node name, list of out neighbors. For this particular course, we're going to use our graph nodes as being symbols. Totally useless. In reality, each node may have a name and then a large number of values associated with it. For example, if we were doing a graph of like the streets, then each node might be something like a destination, and we might include information about that destination. And what's really interesting is that in our examples here, edges have no information associated with them, but in the real world, edges do have information associated with them. For example, the edge, i.e. the road between Waterloo and Toronto, we might want to know information about what is the length of that road. I might want to know what is the speed of that road. I want to know how much congestion is on that road. All kinds of things I might want to know. Edges in the real world often had information associated with them in addition to the nodes themselves. We're going to keep it simple, and we're just going to represent everything as symbols. Okay, so here we have our definition for graph G. So this is the representation in our list of list forms for the graph you see pictured. So you'll see for node A, we have a list that is a pair. We have the name, which is uppercase A, and then we have the list of out neighbors, C, D, and E. And then for B, we have out neighbors E and J. Now you'll notice that node C has no out neighbors, and so its out neighbor list is empty. Make sure that if you're creating a graph in one of these directed acyclic graph formats using an adjacency list, that even if you have no out neighbors, you don't just leave it as an entry C. You actually have to represent the fact that the list of out neighbors is empty. So make sure you're putting empty there. All right, so there is our data structure for this graph. Okay, what else are we going to do with this? Well, obviously we're going to need a data definition. It's not enough to say, oh, it's key value pairs. Yes, by the way, I realize this adjacency list is absolutely totally an association list. Remember what I said about abstract data types? You can use them to implement all kinds of other abstract data types. So here's our data definition then for a graph. For our purposes, we are saying a node is a symbol. We're keeping it very simple here. Then a graph is one of two things. It is either empty or it is cons, and this is our key value pair, a node V onto a list of nodes. And you'll note here that it gives you a bunch of specifications of what this means. And again, this is consing a key value pair onto a graph G. So we say G is a graph, and V and all these W's are nodes. V is the in neighbor of the list of nodes, and V is not an in neighbor anywhere in this graph G. So that is our data definition for our graph. And again, this is just a slight modification to our association list. It's kind of cool. Now, obviously then, we need to create a template for working with a graph. So there are two cases. The first case is that the graph is empty. We should do something with an empty graph. We can't do anything with an empty graph. It's the base. But we don't know what the base case is, so we leave it empty. Otherwise, if the graph is not empty, this should be an else here, by the way, then we are presumably going to do something with the first node, that is maybe node A, and then we're going to do something with our out neighbors. So this is do something with this node, do something with this node, and this is do something with your out neighbors, and then we need to process the rest of the graph, which means we're also going to need a template function to deal with our out neighbors. Well, what could we do with that? Well, maybe we just want to count the number of nodes. So one of the things that you could do to have the list of node template, I'm going to give us some space here. So let's make our list of node template. And it's going to take our list of neighbors. What are we going to do with this list of neighbors? Well, if the list of out neighbors is empty, space case, we'll do something with it. Otherwise, we're probably going to do something with the first out neighbor. And then we are going to call list of node template on the rest of our neighbors. Now, for the record here, you might have been expecting some mutual recursion, and I understand that you might have been expecting that. But we may not be doing mutual recursion either. So I think this is actually a very accurate. Many graph algorithms, by the way, do use mutual recursion. And that is included in this template, because what could we be doing with the first of our neighbors? Maybe we'll be doing something with the rest of the graph with the first of the neighbors. We don't know. But maybe we're not going to do something with the rest of the graph. So I think this template is more than sufficient for our list of neighbors. All right, so we've got a data definition for our graph. We've got a graph defined, and we've got the template. Now let's actually do something with a graph. And if you go to slide 9, they jump right into doing paths with graph, which is, I mean, it's not a hard problem, but let's do something easier with a graph. For example, what I want to do is I want to write a function that is going to count how many edges exist in a graph. That is, given a graph like we saw on the slides, I want to know how many edges are in that graph. So I have that graph, by the way, put up here. I'm going to delete this template for now. So let's bring this back up. So here's my graph. It's the same one from the slides. And I want to count the edges in the graph. Okay, let's think about this. If my graph is empty, I have no edges, so I should produce 0. Otherwise, well, I want to count the edges. The edges is counting in total how many out neighbors does each node have. Okay, so what I'm going to do is I'm going to add the number of neighbors that I have, the out neighbors I have, so that's this first part, to the result I get from counting the number of edges in the rest of the graph. And then my count out neighbors function, if my out neighbors is empty, I produce 0. Otherwise, I add 1 for each neighbor that I have. It's great, right? It's pretty simple. Technically speaking, you could have just called length here, by the way. But, you know, we never let you call length and all of that business. All right. So now I am adding how many out neighbors this node has, and I add that to the result of counting the number of edges in the rest of the graph. So if we call this function on our graph G, we get 11. And if you actually go back in the slides and count manually all of the edges, you will know there's exactly 11 edges. And make sure, of course, our base case is considered. So count edges. Let's do empty. There are 0. What about I just want to know how many edges a graph containing only A, C, D, and E has? So we could do count edges, and then we're going to do list first G. Oops. Apparently I can't spell. There we go. So the subgraph that is A connected to C, D, and E has 3 edges, which is exactly what we expect because A has 3 out neighbors, which means there's a path AC, AD, and AE. So that's 3 edges. So there you go. There is a very simple function that consumes a graph and actually visits all of the nodes in the graph and does some work with it. And it follows the data definition and it follows our template exactly. So a nice simple example there. And we'll do another one next class as well. So then just to briefly introduce you to the topic we're going to go on to next, we want to talk about finding a path in a graph. And this is probably one of the most important things you'll ever do with graphs is finding paths. Because if you were trying to route network data from you to some destination, that's what has to happen. We have to find a path from you to your destination. Number 1, we have to determine, does a path exist? And number 2, if multiple paths exist, which of those paths is going to be the best path? And what does it mean to be the best path? Well, that could be what is the cheapest path, what is the shortest path, which not necessarily the same things, which path doesn't take you through countries you don't like. And if you're sitting there thinking, is that a thing? Yes, that is totally a thing. It's even so much as this company doesn't like this other company, so they won't route traffic through them. But this is also thinking of finding a path. It's like, how do I find a path from my house to your house? There are lots of paths. Well, or maybe there isn't. Maybe you live in the middle of a woods and there is no roads connecting you to me. So finding paths is super important. And what we're essentially going to do to find a path is we're going to create this function called neighbors. And what neighbors is going to do is we are going to use neighbors to help us find our paths. And we're not going to do it right this minute because we are reaching the end of the lecture, but we will do it next class. So next class, for the record, is going to be our very last CS135 class. We are going to finish up our discussion of graphs, and hopefully I will have some more information for you as well on your final assessment. We will obviously be posting all of that information to Piazza as well. So next class is the last one. That will be Thursday at 10 a.m. And I hope that you are all staying safe and healthy and aren't going stir crazy. So I will sign off for now.